Hey, good morning, good afternoon. Welcome to our 37th edition of the ADB Green Roads webinar series. My name is Rebecca Stapleton. I'm a Senior Transport Specialist at the Asian Development Bank, and I will be your moderator for today's webinar. Today, we are going to be covering the topic leveraging satellite data and AI for climate resilient route planning and alignment. This webinar will demonstrate how satellite imagery, remote sensing, GIS, and AI-driven route optimization can be used to identify feasible corridors, assess terrain and climate risks, and develop more resilient, cost-effective road alignments. Through real-world case studies and practical examples, you will gain insight into these innovative approaches that will improve decision-making, reduce project risks, and support sustainable transport infrastructure development from the earliest possible planning stage. Before I continue to introduce our speakers, please allow me to share a couple of housekeeping announcements. The webinar is being recorded, and the recording along with the presentation will be available on the ADB Knowledge Events page, which my colleagues will share in the chat box. To ensure a smooth session, we have muted your microphones, but you will have time at the end of our speakers' presentations to ask questions. You may also submit any questions that you have through the Q&A button at the bottom of your screen, or when you click the More button with the 3 dots. So please submit your questions at any time during the presentations, and we will try to get to those during the Q&A session after the presentations. Our speakers today are Neil Dale and Alpha Pareño. Neil is a senior road design and earth observation specialist at Anyway Solutions with more than a decade of experience in climate resilient transport infrastructure across Africa and the Pacific. And Alpha Pareño, who is a civil engineer and roads and infrastructure design specialist at Anyway Solution, is also joining us and has supported route alignment optimization and feasibility studies in Papua New Guinea, as well as previous work with the Public Works and Highways Department here in the Philippines. So without any further ado, it's my pleasure to hand the virtual floor to Neil. Thank you.
Good morning, everyone. Yeah, so let's get started. Let me just share this quickly. Okay, yeah, Rebecca, you can see that?
Yes, we can. Thank you.
Okay, perfect. Hi, everyone. Good morning. Thank you very much for the introduction, and thank you, everyone, for joining from wherever in the world you are. I'm joining you guys from a cold and gloomy Cape Town. Yeah, so let's get started. So the presentation today is looking at leveraging Earth observation and satellite data and some AI techniques for route alignments, especially in developing nations and for greenfields road development. So what are we going to cover? So first, we're going to look at what is Earth observation. We're going to understand what it is and its applications, and then simple methodologies, tools, and techniques that we use to solve very common problems that we find in developing nations, especially when it comes to greenfield roads and developing road corridors in very rural environments. So we'll look at large area analysis, what data we can use, some of the tools and techniques we use there, some of the sources for some of the open sources for Earth observation, and then the different types of analysis, and then we'll go into more high definition use cases for the different data and the different techniques. Okay, so firstly, what is Earth observation? So it looks at gathering any information about the Earth's surface. Some people use drones. I suppose that's a less removed technique for collecting data. But what are we going to focus on here a lot is satellite data. So satellites are very, very good. So there's two basic sensors when we talk about satellite data. So we have active sensors and passive sensors. So an active sensor is radar, called synthetic aperture radar from space, where it sends out radar frequencies and then it receives something back. So it's active, it's sending something and receiving something back. And then you have passive sensors, which is imagery, which is photographs, because the sensor just receives and it's the light reflected off the Earth's surface. And from there we can derive a lot of information in these rural places where other data isn't available. So the first thing that we do is we look at first collecting the data, and then when we assessing it, we look at elevation, we look at slope, something called topographic wetness index, and then we do run some hydrology analysis. So we look at streams, flooding events, and then we go out and decide where do we need the more high definition products. Um, the next step, it goes on to route optimization analysis. So we then run through many different iterations of this pretty standard process for us. Um, One of the things is where are the people that need to be connected? I mean, that's why we build roads, right? It's looking at where are the people and what's the most efficient way to connect these communities that live in rural, isolated places. So we go and find the people, and then we look at the road parameters. We set up our no-go areas, and then we use a tool, an AI tool that then will run and find the most efficient route between 2 points to connect these people. And then it goes into a design stage where we essentially fine tune everything. We look at the hydrology, the hydraulic structures that need to be built, and then we can create alignment and pull all the data out there for the client so they can see what is the cost. And because we're looking at such large areas, you can do it for multiple options, and then you can compare the differences in those multiple options that'll help you make a better decision on where to put the road. So open sources. So we basically use sort of we essentially use three sources of data. So the first one will be terrain data. There's some very good open sources out there from about 30 to 90-meter resolution. There's many sources out there. NASA has products, ASTA has products, the Japanese Space Agency has products. All of them are pretty good and forever improving. These things are going through iterative cycles, and every few years, the provider provides a new, more updated, more accurate version. The other sources that we use quite a bit is synthetic aperture radar. Um, SAW is it's a very niche field. There's not a lot of people that use it, but so what we use it for mostly is for surface water mapping. So you can see, so this is an area in the Philippines where we looked at. So you go back in time, you look at the news records, and you find reports of flooding. We can then go back in the record and find when these floods were, and we can process the data to understand where are the flood extents, and then we can compare that to where they are during non-flood events. It's very, very good in this use case. You can do the same thing with imagery, but generally around the timing of severe flooding, there's a lot of cloud. Uh, and of course, imagery, you can't see through cloud, which is where SAW is very good because it works at night, it works through cloud, it can penetrate all of that. So you can get good data around the time of flooding, and it helps you to understand where the water is. And obviously, the best case, you know, the best practice that we found is just to try and avoid the flood, is to try and fight than to try and fight nature. Um, then we look at imagery. The European Space Agency and Landsat has pretty big data sets through many different time periods. There's multispectral imagery as well. which you can use to derive a bunch of indicators from. You can look at vegetation. You can identify built-up areas, land use, land cover mapping, urban growth, and because they run on pretty long time scales, you can see how development has expanded and changed over time. The other source we use is his rainfall data set. So generally, when we come to these very rural areas, rain data is very few and far between. The the stations are not continuous for long periods of time, so statistically, it becomes quite difficult um, to understand where, what is your 2% AEP, your annual exceedance probability, things like that. If it's only been running for 10 years, and we also look at sort of to try and see if rainfall is increasing, is it decreasing, is it moving. So we generally try and look for high definition data sets. So one of the ones that we use is a data set called Chirps. So it runs from 1982, I think, until present. So they use satellite data to look at clouds, and then they infer rainfall from the cloud density, and that in their data processing, they ground truth that with gauges that are part of their network, so that they can calibrate their data to actual rainfall data. And it's very, very, very interesting information that we can get out of that. So, okay, so once we have the data, then it sort of comes into how do we start assessing it. So we do very, very large area assessments. So in this map, the pink is roads, which is, you can get that from open street maps. You can get it from the local agencies. Generally, we've found that street maps is, more complete than local sources. Again, all of this depends on, and this method is focused on finding data when no other data is available. So in a lot of developed nations, they have countrywide LiDAR data sources for terrain and things like that. They have complete data sets that you can access and download. What we found in a lot of rural environments is the data simply doesn't exist, or it did exist once and nobody can find it again. Data storage systems and management are lacking in some of these places. So it then comes to, if you have no information, how do you get information to understand the problem and then to best solve the problem? So we look at the terrain, we look at the elevation, we then look at the slope. Of course, you want some slope um, for drainage purposes, but you don't want too much slope because then cutting and filling and road construction becomes expensive. So it helps you to understand where the very flat areas are, where the very steep areas are. We're more looking here, it's a process of elimination. What areas do we want to avoid completely? And then find a way to connect roads in the optimal space. So this is an indicator called topographic wetness index. It just runs on the underlying elevation model. Um, And what it does is it looks at the pixel and it looks at the sum of the slope and number of pixels above each pixel. So you can think about it here, and it's just a dimensionless index. So a bigger number is more susceptible to flooding. So essentially what this does is it finds areas of potential flooding. Whereas there a large area with a high slope that comes down to a pixel that has low slope, because that's where your flooding is most likely to occur. So again, it's just another check for all the other things that we do to try and understand where is it likely to flood, what areas do we want to avoid. And then we do a standard hydrology analysis where we find the streams digitally. We can map them out, and then once you go into road design, you can then do more analysis on the streams once you've built them digitally to understand how many river crossings there are, what is the catchment area for each river crossing, and then peak flows. So this is what the Chirps data set looks like. Um, it's on a 100 meter by 100. Oh, sorry, it's a 5 kilometer by 5 kilometer pixel. So what it does is essentially we found the more rural you get, the more dispersed um, the rain gauges are. And then so standard methods of using a Thiessen polygon or something like that gives you very skewed results because the distribution of that rainfall varies very highly, especially in high rainfall countries and in changing terrain. Rain obviously generally sticks to the mountains. So you can very quickly understand where the rainfall is and how it's distributed across a catchment area or a terrain. So then once we understand where not to build the road, we generally work on a 5 kilometer corridor, and then we go out and acquire high definition products. So there's quite a lot of suppliers of high definition DMs. You can build your own if you want, if you have the time and the processing capabilities. Um, and then high definition imagery as well. The high definition products just help you to see everything better. Um, and it gives you more accurate. They're a lot more accurate than the free low resolution products. And of course, so every time every step of this type of analysis, you go from low cost, low accuracy, large areas, and every time you come down, you step closer and closer to what you want: more definition, more accuracy, and that's sort of the approach. And then you just keep iterating the process. So this is just an example of what free Landsat imagery looks like, which is a 10 meter pixel, and then also what the half meter pixel looks like of the exact same place. And then this is what the just to give an idea of a 30 meter DEM looks like. This is SRTM data, and then what the high definition 6 meter resolution product looks like. So you can see, again, this is the exact same place. Um, it's more accurate. It has a lot more definition in it. It helps you to delineate the streams more accurately, and then you can also it gives you a better idea of what the actual cost is of cutting and filling and earthworks. And then once we have the products, so one of the tools we use is just AI that just goes and goes through all the imagery to find the population centers. So as with everything, there are pre-trained models available, but it's very sensitive to where the model was trained. So I know there's a lot of talk about AI, but it's not quite as smart as what everyone tells you it is in certain applications. So what we have found, so in areas, so for instance, this was done with a pre-trained model that was trained in Indonesia, and we are assuming that the data it was trained on was mostly metal roofs. So in places like Papua New Guinea, where these rural communities use traditional building materials, and once you have the model and you go into a new area or new terrain or a new country, either retrain a new model or you just use your previously trained model as a base, and then you can just retrain it and just add to it. And it finding very, very rural people. I mean, you're working with a 50 centimeter pixel. There are higher resolution imagery products available, but it comes down to the size of the data, because obviously there's a downside to having more data. It's slower, it's harder to process. Centimeter is more than enough to identify landform features, buildings, roads, things like that. And even then, in the middle of the forest, you'll see this tiny little red speck after you've analyzed it, and you zoom all the way in, and sure as hell, there's a very, very small, maybe 2 by 2 meter structure standing in the middle of the jungle. Um, so yeah, we do validate our models, and they normally run between about 75 and 80% accuracy, which for us is good enough because we're not really that interested in every single individual house. We are looking for clusters of structures because that would indicate a village or a community or something like that. And then we can route the new road close to the community. Obviously, you don't want to go and build a new road through the middle of a village, but you can get it close enough to the community so that they have access to the road within generally, 1 or 2 kilometers at least. Um, so yeah, so that's what we use the imagery for, and our pre-trained AI models. So once we have the terrain and the imagery, and we know and understand where the people are, then it becomes sort of a similar process to designing a road as you would during a preliminary design, except you're basing it off satellite data just to get a high estimate of the various options, the different routes, and the costs associated, and the possible pitfalls of those before you then go into an actual preliminary design phase where you do geotech, where you do traditional surveying for the accuracy. Um, so yeah, so once we get to that phase, then for that phase, I'm going to hand over to Alpha.
Thank you, Neil. So, in this phase of our analysis, like Neil said, we already selected our 5-kilometer corridor. And in this phase, we will try to use an AI tool to determine the possible alignments. But the AI would only be as good as our input. So the first thing that we will need is the actual road parameters that the AI will use to find these optimum routes. So when working in the Philippines, the most common criteria and guidelines is from the Department of Works. So we need the road classification, design speed, radius, and maximum and minimum grades, and also cross-section widths and cut and fill slopes and how much it costs. So how we input these parameters in the AI is we try to be a little bit more conservative. For example, in selecting the maximum grade, if the grade is between 10 to 15%, we try to tell the AI to look for alignments that has a maximum grade of 10%, so that when we get to the actual design, we have that room to play around with. We can adjust the grade so that it will suit more our design. Next slide, Neil. Yeah, and the next parameter that we will look for is, because it is quite a wide corridor. It's a 5-kilometer corridor. We don't want AI to put a road where we don't want it built there. So we identify these no-go areas. So usually these are our rivers or the frequently flooded areas. So we can use SAR to identify these areas, and also those built up areas we can look at. If there are areas that we don't want disturbed, we can um, we can avoid those as well. And usually we run the tool for 20 kilometers. So if you can see the imagery on the right here, these two towns aren't connected by anything. So that's usually where this tool comes very handy. And it's also very handy when it comes to very complicated terrain. So it will help us narrow down the alignments that we want to investigate further. So on the next slide. So once we have those parameters in place, uh, we will run the digital elevation model along with the parameters, and the AI tool will locate these possible routes. It usually gives us 3 to 5 possible routes. It depends on the how complicated the terrain is. And of course, if it's a flat terrain, it will usually just give us 1 or 2. But for a more complicated terrain, it usually gives us a lot more options to work with. So on the next slide. So in choosing the terrain that we want to further investigate, we can also look at it in the 3D representation of the terrain overlaid by a satellite imagery so that we can assess more what alignments we want to investigate and how it looks like. On the next slide. And on the on how we design these alignments, it's typically the same traditional design that we do for a detailed engineering design. But because of the digital elevation model that we use is only 5-meter resolution, it's only good for planning and feasibility study phase. So we will still be needing to input the design speed, draw the cross section, minimum radius, and also do the horizontal and vertical alignments normally. Next slide, Neil. But in this phase as well, uh, we will we are optimizing the vertical alignment. So like I said, we manually do the horizontal alignment overlaid on top of the satellite imagery so that we know that we're not running the road on someone's backyard or something like that. And when we get to actually designing the vertical alignment, we run an optimization tool that helps us balance the cut and fill earthworks. So it results to a more uh, economical alignment. So in a very, very complicated terrain where there's a lot of different slopes along the terrain, this tool really comes in handy. We tried to beat the AI. We are designing a 20-kilometer very complicated terrain, and we tried to beat the cost that the AI got, but we can't really get near as close to what it got. Maybe on a flatter terrain, we can beat the AI, but on a more complicated terrain and a longer alignment, it does does a better job. But we can't use the AI standalone. We There are also some minor tweaks that we can do. We can do multiple iterations of the alignment until we get the most efficient alignment. Next slide, Neil. And we do that for all the alignments that we want to investigate. And then once we have done everything, we can compare them side by side. We can compare the how complicated they are based on the number of curves and also the earthworks cost. But again, I want to uh, reiterate that these quantities cannot be used in the actual construction because of the underlying DEM that we used. So this will just help the planners in identifying where to do the actual detailed engineering design, do the actual geotechnical investigations, and how complicated each alignment would be. And on the next slide. And to further investigate how complicated each alignment is, we delineate the streams on a larger, lower resolution DEM. We then take the stream intersections between the streams and the road, and those intersections would be the possible culvert or bridge locations. And for each intersection, we can compute each catchment area and do some hydrological analysis. And on the next slide, and we can compute based on the catchment area of each intersection, we can compute what structure needs to be built, if it's a bridge, a box culvert, a pipe culvert, or we can then in this even in the planning stage, we can determine the diameter size of each culvert, the number of barrel, and to see just how complicated building each alignment would be, uh, and how many additional hydraulic structures would be needed for each alignment. Next slide, Neil, please. Yeah, and then once we have done all of that, we can uh, select the most efficient alignment. We can pull out all the data and see and compare them side by side. And this is what we give to the client. And like Neil said, this is extremely useful in very rural areas where two very disconnected towns uh, don't have any roads connecting them. So instead of the client going into the field and uh, do some ground assessments, do some ground survey on a very large corridor, and then uh, they end up spending a lot of money, and then they discover that no alignment could be done in that area. So this kind of workflow really benefits those cases. Next slide, Neil. Yeah, and since we did all of it in the traditional way, we can pull out the plan and profile maps, and also the cross sections would look like. But again, the DEM that we used aren't really isn't useful for actual construction work. So that's it, everyone. So thank you guys for listening, and I hope you guys learned something. And if you have any questions, just let us know. Thank you.
Okay, excellent. Thank you very much for your presentation. Just pulling up the Q&A box now. Okay, so we have one question there in the Q&A box, and I would encourage other participants to please submit any questions you may have. So, which AI tools will be more accurate during the route and design stage? Is the question in the chat box.
Yeah, that's one of those that you'll have to play around with. I know Autodesk has one. I know Bentley has one. So it comes down to trial and error, testing it, checking it. Like I say, we've tried to beat them in very challenging terrains. You don't even get close. You're off by a few 100% if you're looking at earthworks volumes. In these, look, when you're talking in a flat area that's open, and it's almost one of those when you go to a restaurant and there's 100 items on the menu, you don't know what to eat. If you go to a restaurant, there's 5 items on the menu. It's very easy to choose. So in most places, you have an established right of way, or it's very short. It's it's tightly constrained. But when you're looking over long distances, I mean, we're talking, a few hundred kilometers, uh, finding finding that connection can be very, very tricky. And then so to find the most optimum route for that is quite difficult. In most places, essentially all these models are doing is, so if we look at how roads were developed, over the last, I don't know, few thousand years, they were first goat paths, and then they made them slightly wider into wagons, and then from there, this sort of the road between the communities was built up. But there are still places in the world where it's completely disconnected because of the terrain, and that's where it really shines. So it's just essentially sending a million goats over a terrain and having the goats find the most efficient path. It's essentially just doing that digitally and finding the path of least resistance and lowest cost. So to find how accurate, like I say, there are many options out there, and to assess which one works the best is something that you just have to play with.
Okay.
Mhm.
We've got another question in the chat box. So, can this approach be applied for existing roads that need rehabilitation?
So it can be, if I wouldn't say more rehabilitation, because rehabilitation implies that you're just improving the condition of the pavement. But when the road is being upgraded to a higher standard, where you need to, increase the size of the horizontal radiuses and decrease your vertical grades, yes, it can be used for that. And of course, in the back end, you can look at the cost associated, land acquisition, um, things like that, and then compare. Okay, well, we might spend more on earthworks working within the established right of way, or it's going to be cheaper to establish a new right of way and purchase the land that way. So, and because you can look at it on a wide area, it gives you a pretty good idea. So if you're constrained within a right of way, it's so narrow. Every country is different. You could just, use LiDAR, and then you have the very high definition, um, high accurate data that you need, that you can do your preliminary and your detailed design on. So it all comes down to the use case. It depends on the terrain. It depends on local regulations. It depends on how many people are living next to the road and the area outside of the existing right of way. Um, so sometimes what we've seen is, in these rural communities, everybody lives on the road. Okay. So if you need to move the road within right of way, you need a lot of people to move. Whereas if you're going to establish a new right of way where nobody lives, it might be cheaper to do it that way. So it all comes down to the use case. It's just another option, I suppose.
Okay. Um, Another one for you. What objective function is the AI seeking to optimize when it runs to generate an alignment? Is it to minimize cost, minimize
Yeah.
risk, maximize EIRR, or something else?
So what it is looking for when it's finding the most efficient route, it's essentially running cut and fill analysis, earthworks cost, because that's generally the bulk of the cost of the road. And you can constrain the cost however you want. So you can say, within this area, we know it's swampy, so your cost is going to be more than if you were to go in this area. So it really does come down to how you constrain it. You can say, if it goes through this area, the land is going to cost you X amount per hectare to purchase. If it goes here, it's already government-owned land, it's free. And it can do that cost analysis iteratively. So that's what it's looking for.
Okay, great. Um, what data is needed for training the AI model in a new country or region?
So I'm assuming that question is referring to the building identification. So all you need is satellite imagery of that region, and then you just sit and select buildings from different areas. Are the houses in open terrain? Are they in mountainous terrain? Are they in forest? Are they in vegetative terrain? Is it urban? Is it rural? And you build your sample from there, and then you just retrain. You just train it on that, and then do a test run. And if you see it needs more training, you just keep training it.
Okay. Um,
Yeah.
sorry, we've got quite a few coming in. So, when combining AI with satellite data for terrain analysis, how do you manage and validate ground truth data in extremely remote areas where physical validation is nearly impossible?
It is impossible. Yeah. So you put your faith in again. So what we're doing here is we have done areas where we've compared the digital elevation models to LiDAR data. And the flatter the terrain is, the more accurate it becomes. You're talking within a few centimeters. Once it becomes very, very steep, it becomes meters, right? So that accuracy, doing this type of work, you're not trying to say this is exactly where the road needs to be designed. You're trying to find the most likely location where the most efficient road can be built so that you focus your efforts. That's what you're trying to do. And so when you're doing the comparative analysis, you're just going, this this route is more likely to be more efficient than that route, so that you can focus your efforts. And then from there it becomes traditional surveying, traditional when you're looking at, like I say, it's very large areas, very long distances. The variation within these, even within the options that we find, are often kilometers apart. So from there, then it becomes a traditional exercise, as you would do if you're establishing any new cut track or road or path or thing like that. But it's like I say, we have checked the digital elevation models. We have checked it with LiDAR data in some areas, and definitely the flatter the terrain is, the more accurate it becomes. And also, when you're creating the digital terrain models, it uses algorithms. And like I say, these are all done by third-party providers to strip the vegetation off the terrain. And to do that, it needs bare earth. So the more vegetation and the higher the vegetation gets, the harder it is to get a clear view. But relatively, if it's bad in the DM, it's bad on the ground. But if it's good on the DM, it's good on the ground. But where exactly the good area lies, there's margin for error there. Yeah.
That links very nicely into this question, which I'm not sure, if you can answer, but does the AI consider the environmental impact, including the trees that may be in the way? So you just said it strips a lot of that out. So, um,
Yeah.
yeah, how do you deal with that, the interface with environmental impact assessments and so forth?
So generally, we can look at. So I mean, there's a few ways you can look at it this, right? So if you're going through complete virgin forest, it's virgin forest here, it's virgin forest here. So where you put the road, the impact is generally going to be the same. But a few of the other things you can look at the number of streams that you are crossing for one route opposed to the other route. One, it's a lot cheaper to build less bridges, but it's also there's less impact on those water courses. The less times you have to cross it, the less culverts you need to install. Um, you can look at protected areas. You can do some, there are some data sets of different data sets available saying, like which trees are there. There's more advanced analysis you can do if you really want to do a deep dive with hyperspectral imagery. There are people doing research on it where you can actually identify tree species from imagery. It's still very new, but like I say, the rate at which all these types of analysis methods are improving, it's always improving. So I'm sure in the future you'll be able to get a pretty good data set of, what species of trees are where, things like that. But at the end of the day, if you're building a new road through virgin environment, it's you have to clear trees to build the road. And So, and because of the way we do it as well, we can also, from the cut and fill analysis, we can assess the footprint of the base of the road. So you can go, okay, if we use this road, we only have to clear, 1,000 hectares. If we use this road, we only have to clear 800 hectares. So that's also something that can be considered.
Yep.
And again, it comes down to each individual um, investigation.
Um, Sorry. So I'm conscious of time. We probably only have time for one or two more questions. There's one here. Can this technique predict how maintenance costs for a given road will change depending on the route due to future landslides or flood risks?
So what we do is we look, so maintenance cost is very tricky because so this is very early in the phase, right? So once it goes into construction and there's a detailed design done, depends how bad, good or bad the road is built. I suppose that's also, what material is being used, if the pavement is correctly designed, if the construction. So, but one thing we use the imagery a lot for as well is to identify this even so we can look at these areas and we can find, newly formed landslides, and you can even quite clearly see um, old landslide scars. And generally they happen. We actually just did one a few months ago where there was this whole region that just formed this absolute, I suppose you could almost call it like a caldera, where it was just landslide on landslide on landslide on landslide. So you can avoid these areas. We just go absolutely not. We're not putting a road anywhere near that because that is going to be a problem down the line. So you can look at these images. You can even go back in the because it's quite nice if you're in a forested or a heavy vegetated environment. A landslide shows up on satellite imagery, even on very low definition imagery. It shows up beautifully. So you can go back in the archive of the freely available products, that have been going for 20, 30 years. If you see here could be a problem, you can go back in time and look at, and generally landslides will keep occurring in the same place. It comes down to the geologic structures and the slope as well. That's another reason we look at slope. We try and avoid these very, very steep slopes, not to be near them, um, just to try and avoid that landslide risk, especially in areas with seismic activity and things like that. So that's one thing that we look at quite a bit is looking at the historic landslide occurrence in an area, and we just try and avoid those areas.
Yeah, very well answered. And a good point that, maintenance costs are impacted by so many different factors, right? And we want to make sure when we are going into that DED phase that we're looking at those life cycle cost impacts. Um, there's a question here. Have you had the chance to collaborate concretely with ADB? I don't actually know the answer to that. And if so, was satellite
No,
technology leveraged? Okay, so the answer is
no,
no.
no.
That's an easy one to answer. Um, Another one here, there's some very good flood risk models available. Can these be overlaid into the process?
You can. There are some flood risk models. Um, when it comes down to flooding, it's it's very tricky, right? Because normally flood risk models use their own data, and the data sets are also, you have a method it runs in a server, and it mostly, especially if it's a global data set, it runs on freely available data. So they don't have the same level of terrain detail that we go out and get for each product. So it can be used as initial screening, but we if we see a problem, we can even use it to do to build a 2D model and see where these bad areas are. But we generally look at, in the historic record, look at SAR data, where has it flooded, and most of these water courses are ungauged, so nobody knows how much water comes down them. So there's very methods you can use to assess how much water is coming down them. If it's bad, we'll run a simple sort of like a stripped down 2D model just to understand where is the high risk. But generally, the global products, or the one, I can't remember what it was called, that we looked at is it doesn't quite compare to the high definition products that we get when we're doing this type of investigation. But it is a good initial screening tool. We know, okay, here's high flooding risk, just avoid it, just stay away. Especially when it comes down to a rural road, because you can
Mhm.
think to mitigate that flood risk if you're going to go through those areas. It's a very, very high cost, for a gravel road, which is, that's less than 100 vehicles a day. It's going to be a massive, massive cost. So we generally just try and avoid it.
Okay, this will be our final question for today. So you mentioned, you look at historic data and you mentioned flooding a lot, but have you or could you use the AI to detect areas with permafrost failure risks?
I'm fortunate that I, I'm sure there will be a data set available somewhere. I'm fortunate to work in sunny environments, so I've never had to deal with. But I don't think I've ever been to a country where permafrost is a thing. I know what it is, but and I'm sure if you look, I'm sure there are ways you can look at infrared bands to infer temperature. Um, so I'm quite confident somebody has built a model somewhere that you could look at it. But for me, I've never worked in that environment. We've never worked in that environment, so I couldn't even venture a guess.
No worries. Look, thank you so much. It's been a really interesting presentation, and I think that's evidenced by the number of excellent questions and discussion that we've had. So thank you very much to both our speakers today. Before we end today's webinar, I would just like to share a few announcements and resources that may be relevant to anyone who's currently thinking about working on a green road. Um, so the first one is to say that our webinar series will be going on a short summer break. Our next Green Roads webinar will be on the 27th of August and will be about climate resilient road drainage in practice. So drainage design tool and culvert sizing calculator. Registration for this webinar is now open. So please register today by scanning the link that you see on screen or through the link in the chat box. I'd also like to request you to fill out the webinar evaluation form. This is to help us improve future webinars. You can do so again by scanning the QR code or clicking the link in the chat box. This is also your opportunity to submit requests to present a webinar or suggest topics, which can be done in the comments section of the webinar evaluation form, or you can also send us an email. If you are getting value from the webinar series, we'd invite you to join the Green Roads community to receive updates on Green Roads Toolkit and related news and webinars. So again, you can sign up with the QR code or the link in the chat box. And a reminder to everyone that the recording and presentation from today's session, as well as all the past webinars, are available on the Green Roads webinar series sessions on the ADB Knowledge Events page. So again, available on screen, QR code or link in the chat box. And finally, a reminder that the Green Road Toolkit, which is a compendium of best practices to help governments or transport professionals build low carbon and inclusive road infrastructure, is available via the QR code, the link in the chat box, or on ADB Library website. So that is all for our webinar today. I'd like again for you to join me in thanking our speakers, Neil and Alpha, today for the fantastic presentation, and a big thank you to all of you for your great questions. We hope to see you at our next webinar. Thank you very much. Bye-bye.
Thank you, everyone. Thanks for having us
Thank you,
on. Thank you
guys.
very much.